Introduction to limit laws. Goals here, want to understand the limit laws. I'm going to go through the extensive list of them and then show you how you can use them in an example. And then after that, we're going to look at the Squeeze Theorem. And really we're just going to introduce the Squeeze Theorem here and then show you an example of how it works. Really useful for oscillating type functions when you're trying to find their limits. Limit laws overall, they're just useful tools when you're trying to find limits without graphs or tables. You can use them on graphs, but I think the main focus of these things is to get you away from graphs and tables and let you do them algebraically. So why do they work? Why do these limit laws that we're about to see work? Well, if you remember back to college algebra, you had operations that you did with functions, things like add, subtract, multiply, divide. So the limit laws are based on function operations. You're going to see addition, subtraction, multiplication, division. You're going to see those same basic operations come into play. And the reason that these operations are going to transfer over to limits pretty well is because of the idea that limits are essentially just a special kind of function value. They still give you a y value when you're looking at a limit. So the operations that we saw before in an algebra class just going to be modified here to work with these limits that are still basically y values. And you can prove these laws using the precise definition of limit. Not going to do that here, not going to worry about it. So the limit laws that we're going to use in this class are as follows. And for all of them, assume that c is a constant and that the limit as x goes to a of f of x and the limit as x goes to a of g of x exist. So let's take a look at the first 5 here. Okay, so the first one, the sum law. This says the limit as x goes to a of f of x plus g of x can be found by just taking the limit as x goes to a of f of x, the limit as x goes to a of g of x, and you add those together. So basically, the idea is that you are just doing the limits of each function individually and then adding the results together. That theme carries through the other 5. Difference law, same thing. If you want to find the limit of the difference of the functions, you do the individual limits first and then subtract the results. If you're multiplying a function by a constant and want to find the limit of that, you can just find the limit of the function and then multiply that result by the constant. If you're doing a product of 2 functions and you want to find the limit of that product, you can do the limit of the individual functions and then multiply those together. Same thing with the quotient law. You want to find the limit of a quotient of 2 functions? Well, you could find the limit of denominator, limit, and then you just divide them. And this one, if the limit of g of x is equal to 0, you're just going to say it doesn't exist at this point. So they have that little stipulation there where the limit of the denominator can't be equal to 0. But basically, the whole theme throughout all of these is that you can look at the individual pieces, find their limits individually, and then combine them with the operations. That's the main idea of the limit laws. All right, so let's look at a couple of other ones that kind of follow from these, or I should say several other ones that follow from these, and the 6 through 9, they'll be the last ones that we'll see here, but let's go ahead and see what they are. Okay, so the first one we'll look at here is the power law, and for the power law, what we're basically going to do is take the product law, let the g of x equal f of x, and think about the idea that if you multiply things repeatedly, you can represent that as something raised to a power. So the limit of that f of x raised to a power, multiple f of x's multiplied together, can be found by just doing the limit of f of x first, then raising the result to a power. So still that same theme of finding the individual limits and then doing the operation on it. And in this case, for this law, we're just using n as a positive integer. So the powers are going to be, 1 technically, but boring, and then 2, 3, 4, 5, 6, etc. Next one, the constant function law. For this one, if you are taking the limit of a constant, it's just going to equal that constant. And if you visualize what a constant graph is, it's a horizontal line going through the y equals c value. Well, the limit, no matter what x value you're approaching on a horizontal line, is going to be the y value that horizontal line is using. So limit of a constant is just the constant. The identity function law just says that if you have the y equals x function, the identity function, then the limit as x goes to a of x is just going to be a. The y value is going to approach the same exact thing as the x value because you're looking at that y equals x identity function. And then last but not least, the root law, kind of a play on the power law in a sense, where instead of taking it to a power, we're now applying a root, but same basic idea. If you want to find the limit as x goes to a of the nth root of a function, you can just take the limit of the smaller piece, the function underneath, and then take the nth root of that. And here we're only going to work with roots that are positive integers, square root, third root, fourth root, fifth root, etc. And if the root happens to be even, if n is even, you're just going to assume that the limit of f of x is greater than 0. So you're still not going to work with negative numbers under an even root radical. All right, so let's go ahead and take a look at an example here. We can take a function, break it down into parts, and evaluate things individually. So for this one, let's let the f of x equal x squared plus 3x, and I want to find the limit of that function as x goes to 1. Okay, so first step, we are going to use the sum law, and I am going to just split up the sum into 2 separate limits. So that's the first thing you do. And then the next thing I can do is I can use the power law. So we can have this limit as x goes to 1 of x squared. And then I'm going to use the product law. So I'm going to take the limit of 3x and split it into a limit of 3 times the limit of x. So from here, I've got things broken down pretty good. I can start evaluating the pieces. And the limit as x goes to 1 of x is just going to be 1. That's that identity. So we're going to have 1 squared. And then the limit as x goes to 1 of 3, that's that constant idea. So we're just going to have the 3 coming out of that. And then we have another identity, so that's going to be 1. And if you do 1 squared plus 3 times 1, you get a limit of 4. So just breaking things down to their smaller pieces and then doing the operations. And note that for this example, you could have just found a limit by finding f of 1. You plug in the 1 and you get 1 squared plus 3 times 1. It looks a whole lot like this right here. And you still get 4. So this concept is called direct substitution. Doesn't always work, but when it does, it's great. So direct substitution. Example of when it might not work would be when you're trying to find the limit of x plus 1 over x minus 1 as x goes to 1. In this case, you try direct substitution and you get 2 over 0, and that's undefined, at least as it stands. So we're going to have to, think about this. We'll see a way to deal with these types a little bit later, but direct substitution isn't going to be the way to get there. It is worth trying first because it can quickly give the limit value. So I always try direct substitution first, and if it doesn't work, then I try another technique. Okay, so let's take a look then at the squeeze theorem. See what this is all about. And what the squeeze theorem says is that if you have this compound inequality where you have the f of x function being less than the g of x function and g of x function being less than the h of x function, so basically the g of x in between the f of x and h of x, and if the limit of the f of x equals a value and the h of x limit is that same value, it forces the middle g of x to have the same limit value. So they sometimes call this like the pinching theorem or sandwich theorem, where like g of x is basically sandwiched between f of x and h of x. And if the f of x below and the h of x above are honing in on the same exact value, that g of x in the middle, it's kind of forced to go to that same value. And this is really useful for some functions that have oscillating behavior. So let's see the example here. I want to find the limit of x squared sine of pi over x as x approaches 0. First thing I'm going to do is split this up into a product. So limit as x goes 0 of x squared times the limit as x goes to 0 of this sine of pi over x. Now the first part of the product, that's fine. We can do that all day long. Second part, this does not exist. And 0 times does not exist does not necessarily equal 0. So we have to do something different than using our limit laws. And that's where the squeeze theorem is going to come in. And the first step is to just take the sine of pi over x part and realize that the sine is between -1 and 1. Even with that pi over x, it's still going to go between -1 and 1. That's not really the function that I want to find the limit of. So what we're going to do is modify the middle by multiplying by x squared. And whatever you do to the middle on these, you got to do to both the left and the right. So we're going to multiply the whole thing by x squared. And we get this -x squared less than or equal to the x squared times sine of pi over x less than or equal to positive x squared. And now I'm going to look at the limits of the left and the right side. And doing those, you're going to get limit of -x squared as x goes to 0 is 0. You can use limit laws to get there. And the limit of positive x squared as x goes to 0 is also 0. So we got the left side of the compound inequality going to 0, the right side going to 0. Squeeze theorem is going to give us the final limit of the middle as also being 0. So the limit as x goes to 0 of x squared times the sine of pi over x will equal 0. And that's where the squeeze theorem is really helpful. Forcing that middle part to be equal to what the left and the right equaled. If we look at this thing graphically, I have the x squared, the -x squared, the red is the x squared sine of pi over x. And if you start zooming in, you can see that that limit is kind of squeezed in between the two, kind of forces it to go to that 0, even though, the other one, the pi over x part on its own doesn't have a result. Using that squeeze theorem, we can kind of squeeze in and see, oh yeah, it's got to be going to 0. It's forcing it to go to 0. So pretty cool to see that on the graph. And if you do have questions about this, please ask. Otherwise, thank you for watching.